Well, good morning, everybody. Here from snowy New Mexico on this winter morning. I'm sure glad to be in here making a video instead of outside. Hope you're having a good day where you are. I was talking to somebody last week about making a video on seismology, and I was so excited about it. I thought, man, this will be a really good topic. And little did I know I was opening up a huge can of worms. So I encourage you to jot down some things, leave them for me in the comments, and if you have questions or whatever, and I'll get back later. First, of course, our joke of the week. I was cesarean born. You can't really tell. So, on with the show. What is seismology? Seismology is the study of earthquakes and seismic waves that move through and around the earth. A seismologist is a scientist who studies earthquakes and seismic waves. Let me emphasize that word scientist. Don't forget, some scientists don't study the stars. Seismic waves are the waves of energy caused by the sudden breaking of rock within the earth or explosion. They are the energy that travels through the earth and is recorded on seismographs. And we'll talk about these things. There are different kinds of seismic waves, and they all move in different ways. The two main types of waves are body waves and surface waves. We won't talk about surface waves. Body waves can travel through the Earth's inner layers, but surface waves can only move along the surface of the planet like ripples on water. Earthquakes radiate seismic energy as both body and surface waves. So body waves are divided into two types of waves. P waves, or primary waves, are compressional waves, the fastest kind of seismic wave. P waves can move through solid rock and through liquids. S waves, or secondary waves, an S wave is slower than a P wave and can only move through solid rock, not through any liquid medium. It is this property of S waves that led seismologists to conclude that the Earth's outer core is a liquid. So we'll talk about those things. Seismic waves are created by the shearing or cracking of rock. This is commonly caused by earthquakes, volcanoes, magma movement, and large man-made explosions, like certain countries that do atomic testing, and even for smaller things, a sledgehammer and a striking plate, or dropping a weight, a seismic energizer, or an explosive charge can work. This would be like if a scientist is doing an experiment for a short distance just to gather some information. I know our buddy Nathan Thomas would be excited about sledgehammer. So Waves and their uses. There are different kinds of waves, and in fact, if you look it up, there's like a whole uh, continuum of waves, uh, and they're categorized by wavelength. Wavelength is a continuous number. So at one point we have light waves or lasers, and light, of course, is what we see, what makes us be able to see everything around us. Laser uses, there's many uses for lasers, and there you can see a whole list of uses. I'm sure you know lots of things that lasers are used for. Sonar. Sonar is basically sound waves. Is a technique used to using sound propagation to navigate, communicate, or detect objects on or under the surface of the water, such as other vessels. So they use it for detecting submarines or other ships that are close by. There are two types of technology. Passive sonar is essentially listening for the sound made by vessels. So passive sonar, you're just taking in sound and processing it. Active sonar is emitting pulses of sound and listening for echoes. So you can use active sonar for looking for fish, whatever you might want to look for. I know I've been watching the Science Channel, and they do a lot of things with sonar and mapping the bottom of lakes, looking for treasure. The next one is microwaves, which incidentally are used for microwave ovens. They're UHF, ultra high frequency. They're used for cell phones, wireless local area networks, and satellite communications. So microwaves are very useful. You use different frequencies for different things. I think we all remember, using different frequencies, and even now you have 4G and 5G and all these things, and they all use different frequencies of microwaves. The next one is radar or radio. This is used extensively in astronomy. It's a technique of observing nearby astronomical objects by reflecting microwaves off of those target objects and analyzing the reflections. The research has been conducted for 6 decades. Radar astronomy differs from radio astronomy, and it's like sonar. You have passive and active observation. Radar systems have been used for a wide range of solar system studies. Radar can be pulsed, or it can be a continuous wave. And then, of course, we have P waves and S waves. They're useful to study the composition of the Earth. They also use those in mining, petroleum industry, tracking large explosions, and the study of seismic events. Electromagnetic radiation exists in a continuous range of frequencies. So each of these types of waves that we talked about can have a range of frequencies mentioned before. Amplitude is the strength of the signal. And amplitude is the part that changes by the inverse square law. So you hear that a lot from flat. I thought I would mention, just because it's in the news lately, there is a planet-wide millimeter radio telescope array now that has 10 times the resolution it had before. And basically these are radio telescopes spread across the Earth that are all focused into one, essentially one telescope, and they can pick up even lower amplitude radio waves. And I'm sure you've heard this in the news, so when you hear it again, this is what it's about. So, seismographs, how do they work? So I have several pictures here that I want to talk about. Up here in the upper right, that's what a seismograph looks like. You have a roll of paper, and the seismic waves make images like that on the paper. It's really fascinating to watch and to see how they know what waves are what. Down here on the upper left, these are the plates, tectonic plates. When you hear about movement of plates, that's what they're talking about. And so you can see the outlines of these different plates, where their boundaries are. Interesting that there's one continuous line there across the Antarctica down there. So keep these in mind, and let's look right down below. There's a picture. The picture below is of earthquakes. So these are the earthquakes that are caused, or that have been measured across the world. And notice how well these earthquakes match those boundaries in the picture above it. So all of these earthquakes are related to the movements of those continental plates. So, and then the next thing I wanted to show you has to do with seismographs. On the right-hand side there is a map of the world, and each one of those stars is a seismographic location. So there are seismographs located basically all over the world, monitoring earthquakes. And we'll get into that a little more. So here are our two kinds of body waves that we talked about, the P wave and the S wave. You notice the top picture is a P wave, and it's a compression wave that we mentioned. You can see how it moves. Basically here it moves from left to right, and there's a compression of those particles. And below that is the S wave, and particle motion is kind of up and down. This is sort of like something you could surf on, right? So that's an S wave. So what do these waves mean to the study of the Earth's composition? Earthquakes and Earth's interior, geologists cannot observe the interior of the Earth directly. I mean, you can't send a camera down there or go down there unless you're on a movie journey to the center of the Earth, right? So here's a picture of an earthquake. You can see where the focus is of that earthquake up there on the right-hand top. That's where everything is generated. And then these waves that are generated travel through the Earth in a straight line until they reach the other side of the Earth. So in the upper left, you can see that there are both P and S waves. And you remember from our map, there are undoubtedly seismograph stations that are monitoring those waves from that side of the Earth. Down on the right-hand side, you can see S and P waves again, and those seismographs are monitoring those. You notice that only P waves go through the center of the Earth, and there is some refraction when they enter the outer core. So we know that that outer core is some kind of liquid, or something liquid. Scientists can tell the pressure, the temperature, and other information about the outer core based on the refraction and the speed of these P waves as they travel through the outer core. And of course, they're monitored by seismograph stations all around the world, so you can see a lot of these places will get information from one earthquake. And then lastly, you have P waves that go through the inner core, and they have been able to tell because of the inner core that it's made out of something nickel and iron, very solid, under a lot of pressure, high temperature, and that's the inner core. So basically you have the mantle, which is the yellow part. The mantle is kind of a plasticky, it's not liquid, just kind of a semi-liquid, I guess. S waves still travel through there. Then you have the outer core, which is liquid, and the inner core, which is very solid. And let me stop here just for a minute and mention that the outer core, the orange part, because it's a liquid, it rotates based on the rotation of the Earth. So as the Earth rotates, it makes that center part rotate as well. You can think of people riding on a merry-go-round, and the outside people, rotate, and then that causes the inside to rotate. So that inner core is rotating. It rotates against the inner core, So that outer core rotating against the inner core works like an electromagnet, and it produces the Earth's magnetic field, which is so important. And that comes from the makeup of the interior. So here are some other pictures let me talk about. Of course, the top one we all recognize as the good old flat Earth. Lots of stuff going on there. This was the only picture I could find that had some thickness to the flat Earth, because I wanted you to think about these waves. Now notice in the bottom picture, this is the one we just saw, that when the earthquake starts at its focus over there on the top right, it sends out waves all across the Earth, all around through the center of the Earth, the surface waves on around the surface of the Earth, and those waves can be detected not just by nearby seismographs, but by pretty much every seismograph on the Earth. And it's the way they can tell that the Earth is spherical is because of detecting these waves everywhere. Now imagine on this flat Earth picture that we have here that an earthquake happens. Where can we pick a spot there? Near the center, let's say in Saudi Arabia there, you can see almost right at the center of the photo. The waves are going to travel basically in a sphere, every direction. So the P waves and S waves that go through the crust or whatever that is of the Earth, they're just going to reach the bottom and stop, and we're not going to be able to detect the same waves in South America over there or Australia, because they're not going to go that direction. They go through to the bottom of this flat Earth plane or whatever. So P waves and S waves, there's just no way that you can monitor those and think about all the different monitoring stations and how you can come up with, that's how it works on the flat Earth too. It just doesn't. So that was pretty much it for the week. And again, let me tell you that leave me some questions. I'm glad to talk about this more on another video. And lastly, here's our joke of the week. I was cesarean born by a cesarean section. You can't really tell, except when I leave the house, I always go through the window. Oh, good, I left a blank slide here. So next week, on Tuesday, I'm going to plan on talking about truthers, and so that should be a good video. And I'm going to not be able to do one next Friday because here in New Mexico it's a holiday, And so I'll be out of town for 5 days. But we'll see you on Tuesday. Be sure to come and be